Okay.
Good morning, everybody. The speaker is Karoly Simon from Budapest, talking from Budapest.
Yes.
And the title is Some Random Self-Similar Sets on the Line. You are welcome.
Thank you very much for invitation for this talk. I would like to say that all new results are joined with Vilma Orgoványi, who is a PhD student under my supervision in Budapest. So what I would like to talk about first, random Cantor sets. So I like to introduce the possible simplest setup where we have two coins. Well, we have one coin. I hope that it's visible, but I go to a bigger screen because now the little details will be more important. I do not refer anything. So there is this coin, the head and the tail, and the probability that it shows up on the head is P and the tail with 1 minus P probability, and we toss it independently in every step. And so let me say that I just show it, all of this thing in a very special case when we divide the square into 3 times 3, altogether 9, this 9 big, this is the unit square, and we divide the unit square into 9 congruent squares. These side lengths are 1/3 for each of them. So first we do that, and for each of these squares independently, we toss this coin, what I showed previously, and this is one possible result. And whenever you see James Madison, then we color it. It means that the square is retained. So this one is retained. But you see the liberty, it means that this square is thrown away, discarded, and there will never happen anything in the future here. This area has died. And you see that in the second row, all the squares are retained, but in the third row, these 2 are discarded and the last one retained. And then what we do that all of these big squares of side 1/3 are divided similarly into 9 smaller squares. And then for each of these squares, we toss the coin again independently. So we do not repeat the pattern, we repeat the method. So this coin tossing results like this, what you see. So you see head 3 times in the first row and at the beginning of the second row and the right bottom corner, and all the other 4 are the liberty, which means that these people died in the second step. And now we would like to see which are the squares among these 9 which are retained now. So we toss the coin, the 9 coins again, and you see here is the head, here is head, here is head, here is head, this and that, and all the others are a tail, this liberty statue, and this means that they died. And we repeat this for this again. For this square, we toss flip all the 9 coins as it is shown over here, and this shape L is retained. All the rest are discarded, and yet again we toss the coins, and then this is retained, and these 4 places are discarded. And then we repeat this independently, and then we stop here. We do not do anything in those squares which were thrown away right in the first step. So now the union of these blue squares is lambda 2, which is the second approximation of the Mandelbrot percolation Cantor set, and the orange, the union of the big orange squares, was the first approximation of this set. And then this picture shows a different realization. While in this case also m is equal to 3, m is always the number how many m times m we divide on each of the coordinates axis, along each of the coordinates axis into m equal intervals, and we take the product. And the probability in this realization was 0.85, so that we got a lot of. Now I go back, because from now on I will refer to various things. So I need some definitions, and that's why I need more screen. So En is always going to be the set of retained level n squares. I would write it down here. I hope that you can see it. So is the collection of retained level n squares. Cubes, better to say, because maybe we will be in higher dimensions sometimes. Okay, I hope you can read what I wrote here previously. So this is En, calligraphic En, and the nth approximation is that we just take all the cubes which are contained in En, and we consider their union, and we call it lambda n, and this is the nth approximation of this random Cantor set under consideration, and whatever remains after infinitely many steps, because this is a nested sequence of compact sets, so whatever remains after infinitely many steps, it is this random object what we consider. We call it fractal percolation set or Mandelbrot percolation Cantor set. And it may be an empty set very well. It can very well happen that whenever you toss these coins, all of them turns up not head but tail, and then you do not retain any square. So it can very well happen that no square are retained. Okay, so it can be an empty set, otherwise it is a compact set. So the fractal percolation Mandelbrot percolation set is denoted by in this way, this lambda dmp. D refers to the dimension. In the previous example, D was equal to, so this is lambda dmp. In the previous example, D was equal to 2, and m is the number. So when you divide the square like 3 here and also 3 on the other, then we say that m is equal to 3. We do not say m is equal to 9, m is equal to 3, and then p is the retention probability, which is over here. So when this set is empty, then we say that this event, because this is an event, this is a random set, it can be empty. We call this event that the set is empty extinction. This happens with positive probability when p is smaller than 1, and we always assume that p is smaller than 1. And then when this set is non-empty, then call it when it is not empty, we call that even non-extinction. And usually all the theorems that we state will be conditioned on non-extinction. So what is the first question what we may ask about such a set is, what is going to be the Hausdorff dimension? And the Hausdorff dimension of this set is the same as the box dimension. And this is given by the formula what you see over here. So the explanation for this formula is that this log m in the denominator, the log m refers to the contraction ratio. So log m is the contraction ratio, the reciprocal of the contraction ratio. And what you see in the numerator after the logarithm is the number of retained squares, or retained, the expected number of retained cubes because each of the squares in this example that I show, if the probability is P, then the probability that you retain such a square that I show here, that the probability you retain it is P, but you have M squared of them, or in higher dimension, M to the power D. So the expectation of the retained level 1 square is what you see in the numerator after the logarithm. So this is pretty much like we are used to the fact that, for example, if you have the usual periodic Cantor set, when this one doesn't exist, just you have 2 and this is 1/3 and this is 2/3 and this is 1, then you know that this dimension is log 2 divided by log 3. And here we are in a very similar situation, because log 3 is the reciprocal of the contraction ratio, and log 2 is the number of these first intervals. And here we have the number of the expected number of the first intervals. So this is the formula what we need. And you can take logarithm only non-negative only numbers. Well, you do not want this expected number to be smaller than 1, because the dimension cannot be negative. And it is easy to see, we will discuss it, that if m raised to the power d multiplied by p is not bigger than 1, then almost surely true that the random set will die out in finitely many steps. I will speak about that a little bit later. Now we come here to this screen. So the Hausdorff dimension. So this was one observation, that if we are in dimension d, this is 0, and here is p. Then what you always need it is that p needs to be bigger than 1 over m to the power d. Okay, now there is another interesting thing. When do you have that the dimension is bigger than 1? It will be important for us. So this is the region when you have a chance that lambda is non-empty, condition or non-extinction, but I don't want to write there. And then when do you have that the set has dimension, lambda has dimension bigger than 1? If you have a look at this, what you need it is that m to the power d times p is bigger than m, in order to provide that this ratio is bigger than 1, what means that p needs to be bigger than 1 over m to the power d minus 1. This is what you need in order to have dimension bigger than 1. Okay. So it's easy to see that the number of retained cubes is a Galton-Watson branching process with this binomial ospheric distribution, and that's why the expected number is indeed this md times p. And we know that if you have a Galton-Watson process and the expected number of children is not bigger than 1, well, the equal to 1. So it can survive if it is equal to 1 only in a trivial case. So in this non-trivial case, that if it is more than equal to 1, the number of children is more than equal to 1, then it dies out in finite steps with probability 1. So the interesting thing is only when interesting case when p is bigger than 1 over m times the dimension, as it is written over there. Now we talk about the percolation phenomenon. The percolation phenomenon. So what does it mean, percolation? The percolation, we say that this lambda percolates if, for example, we have this square. I draw a square again. This is supposed to be the unit square. And then you have lambda, which consists of lots of points. But if there is something like this, so if lambda, oh, you do not see it. So if lambda consists, maybe it's just a moment. I need to try out. But yeah, this is better. Okay. So if something like this happens, then it means that it percolates. So lambda connects somehow. This omega means just the realization of lambda. It percolates. So for some realization, it percolates. Sometimes it doesn't percolate. Maybe if lambda connects the opposite walls of the unit square, then we say that it percolates. And then this is an event. This is a random event, and I needed to find out some way to denote it. And then the notation for this is lambda, and these are the two walls, and here are two arrows, and then so this is a LaTeX symbol, and this means that the set percolates. And then the first famous theorem of this theory, I believe, was proven by Chase and Durrett. They said that there is a critical probability such that if P is bigger than this critical probability, then the set is the set percolates with positive probability, and if P is smaller than the critical probability, then lambda is totally disconnected. The event is totally disconnected. Is denoted by TD, totally disconnected. It means that all connected components are a singleton. At the critical probability, it percolates interestingly. So this was an interesting theorem. And then there have been many other papers which followed this line. For example, Ronald Meester proved that if P is bigger than this critical probability, so if lambda somehow connects the opposite walls, then it contains a path-connected component. And then Chase wrote a survey paper from which it follows that lambda does not contain any Lipschitz curve. And last year, there was a very interesting paper by Zoltán Bucolic, Esha, and Marit Jarvenpa, Tamás Keleti, and Thomas Pölyárt-Hari, I think, who proved that lambda is almost surely purely unrectifiable, which means that this set lambda intersects every Lipschitz curve in a set of zero measure in this sense. So it does not, it is very irregular in some sense. Okay, so this is just and then
this
you can also
reminds me a little bit Smirnov papers about percolations on triangular lattices.
Yeah, there are a lot of connection between
either opens or it
yes
closes the passage from one vertex to neighbor vertices, etc.
a lot of connections to the usual percolation indeed, but there are differences. For example, at the usual percolation, but people this equality doesn't hold. So only for P bigger than the critical it percolates, and for the critical probability it does not percolate as opposed to here. So there are differences also. Okay, so we
may critical equal 1/2.
Pardon?
Is critical P equal 1/2?
Critical P, about the critical P, I just like to say something about the critical P. So it's
there's a symmetry. If you have connection between left and right, then it's the same probability as to have connection between upper and lower.
Yeah, exactly. Yes, but here it just says that with positive probability. So it says that it happens with positive probability. Yes. So it doesn't matter that you want to connect the left hand wall to the right wall or the upper wall to the bottom. It doesn't matter. And about the critical probability, we do not know too much, but there are some results. The best ones I know are from a former student of Michel Decking, who proved that if m is equal to 2, so if m is equal to 2, then just a moment. No, this is not good. Something is not quite good. Sorry. Okay. So if m is equal to 2, we divide along both sides just into 2 parts. Then the critical probability is at least as big as this. If you divide into 3 parts, as we did on the example I showed, then the critical probability is as big as this. And here are some upper bounds for the critical probability. I do not know currently better estimates than this, but it shows that these critical probabilities are relatively big, but the estimates are not very precise. You see, even for 3 or for 2, they are far from each other, kind of. So this is what we know at the moment.
So these are rigorous bounds?
These are rigorous. So these are absolutely mathematically rigorous upper and lower bounds. Yes.
But I still don't understand why this critical for d equal to, why this critical p is not 1/2. If you have connection between left and right, then you don't have connection between upper and lower.
But the complement is not obtained in the same way. Yes, complement looks very different from the set itself.
Ah, well, I don't understand.
Well, complement contains lots of squares. Because if you draw a square,
1/2 is the parameter under which the Hausdorff dimension becomes larger than 1. But dimension larger than 1 totally does not say that there will exist a connected component.
It's a very, very strong.
It's about connected component. It's about joining left to the right. This critical means there is a non-trivial component, or critical means there is connection of left side.
Critical means that if you take a probability bigger than the critical, then with positive probability, you have connection which appears on this picture.
So
The two things are very related. Above the critical parameter, you have probability 1 of having large components. And this immediately implies positive probability of having long components, connecting left to right or up to down. And below critical parameter, there aren't almost surely there aren't any components larger than 1 point, so of course they do not connect anything to anything.
Okay, go on.
Okay, so there is one thing what we need later, as I mentioned earlier, En stands for the collection of retained Leveland cubes, and then what we can write it is this W, what you see over here. This W, which is a random variable, this is the limit of this ratio, where in the numerator you have the number of retained Leveland cubes. Well, if this is m squared, if we are on the plane, but m to the power d in general, and then what you have in the numerator, it is just the expected value. So the denominator is the expected value of the numerator. So the expected value of the number of Leveland retained square in general in dimension d is md multiplied by d raised to the power n. This is the number of retained squares. So what we do here, it is that we divide the actual number, that's why it's a random variable, the actual number of retained square by its own expected value. And then it can be proven that in our situation and in most of the situations, I could not be more specific, but whatever situation you are likely to meet, this W is positive, almost surely conditioned on non-extinction. This will be enough. This will be important later. So this W, okay. Now I would like to say a couple of words about the projection. I think everybody in the audience knows this. There is a question.
It defines what a condition of connection with the right.
It was written after existence of
Karoly, once again.
Okay,
Pardon?
so, yeah, repeat because I was talking here.
I'm sorry, I do not hear the question.
No, go on.
Okay, so this is orthogonal projection. You know what is orthogonal projection. I don't need to dwell about that. And here is the very, very famous Marston projection theorem, which says that if you project from the plane, then the dimension is preserved for the projection of almost all directions if the set dimension not bigger than 1, and if the set has dimension bigger than 1, then the projection has a positive Lebesgue measure, and this is the projection theorem. And about the intersection, but Marston proves that under this condition, what I show here, for almost all elements of the set B, if you draw a straight line across this X, then this is going to, so for almost all straight line, it means that Lebesgue almost all straight line. So you fix it as X, and then you take the Lebesgue measure on the directions, and for almost all direction line across this point X, the intersection between this line and the set satisfying this condition is what it needs to be, namely the dimension of the set minus 1. This is the Marston projection theorem and slice theorem, which are very, very famous theorems. And I just like to mention a theorem of Falconer and Grimet, which is about projection to the x-axis. So if you have this Mandelbrot percolation set, and P is bigger than 1 over M, which we are on the plane. So we are on the plane, and on the plane, D is equal to, and on the plane, D is equal to 2. So 1 over M is D minus 1. So P is bigger than 1 over M means that we are considering a set lambda on the plane with Hausdorff dimension bigger than 1, and you project it to the x-axis, then it contains an interval almost surely conditioned on non-extinction. With Michal Rams, we conducted a research. I will talk a little bit about that in this direction, and this paper was really the kind of the starting point. So they considered only the projections of this Mandelbrot percolation to the coordinate axis. Okay, and then with Michal Rams, we considered other projections, not only the orthogonal projections, but the co-radial projection, which means that if you are given a set and you project it, so there is a center and there is a set. And this co-radial projection centered at T of this set lambda is obtained by projecting the points of this set to the unit circle as it is shown over here. And sorry, this is the I'm sorry, this is the radial projection, so there is no co here. This is the radial projection. The radial projection, when we project on the unit circle centered at the center T, and the co-radial projection is just the collection of distances of the set from this center. So this is the radial and co-radial projection. And then you may have heard at least 10 times our theorem with Mihan-Rams that if P is bigger than 1 over n, so we are on the plane, this means that the Mandelbrot percolation set has bigger dimension, bigger than 1, then simultaneously, then it happens almost surely. So for almost all realization of this set, it happens simultaneously for all direction. The projection contains an interval, and also the radial, this is not co-radial, this is radial and co-radial projection. This co-radial projection is basically the pinned distance set, the pinned at this point distance set. So the pinned distance set also contains interval. This was our paper with Mihan-Rams, and then you certainly have seen this picture with which we want to popularize this theorem, in particular the first part of the theorem, that if you have, let me say, on the plane such a Mandelbrot percolation set, and P is this, the interesting situation is when the probability is bigger than 1 over m. So for example, if m is equal to 3, then 1 over 3, and in that case, the critical probability is estimated here, what you see over there. So if P is bigger than 1/3, but smaller than the critical probability, so for example, smaller than the 0.784, then what you have it is that lambda is a totally disconnected set. So it is a random dust, but from every moment when the sun shines, that in the shadow, you will find an interval. That's how we popularized this theorem. And certainly I spoke about this on the 60th birthday conference of Felix. And if I remember well, Felix as then, or some other times, I don't know, that the sun actually, what is shown here, it is not two-dimensional. So what can we say about the theorem in 3 dimensions? And then that was basically answered by a former student of mine. He is now working for Morgan Stanley, but he was a good student. His name was Lajos Vágó, and myself proved that the theorem, which we proved with Mihan-Rams, at least the first part of the theorem, is valid in any higher dimension. So a very much analogous theorem could be stated for the 3-dimensional case with really 3-dimensional sun shining. Yes, so and one more thing I like to mention, that Mihan-Rams and just a moment, let me go to 30. Mihan-Rams and these 3 slides are about the next topic I would like to talk. Mihan-Rams and Yuval Perez proved something more. Now we need to recall what was W. So I need to go back to formula 4. This was formula 4, and this was W. That you obtain W by taking a big N and considering the number of retained square of level N, and you divide it by the expectation of the same. So the expectation of the numerator appears in the denominator. This is W, and we know that it's positive. So this is just recalled over here. And what is the natural measure on the attractor? You just take the weak limit of the following sequence. You restrict the 2-dimensional measure on the nth approximation, and you divide by the area of the nth approximation. And this is a measure, and you take the weak limit of this measure, and this is mu, which is the natural measure. So this is the natural measure, but we know what is the Lebesgue measure of the nth approximation, because every cube in the answer approximation has this area, and it needs to be multiplied by the number of retained cubes on level n. So you have this. But if you put these two formulas together that I show now, then you get basically that the limit is the Lebesgue measure restricted to the answer approximation divided by p to the n times w, and this is w. Okay, but because w is positive, you can multiply with w, and then you come to this line, what I show you now. This is mu tilde, which is almost the natural measure, just the natural measure is multiplied by a positive random variable. Now, the huge advantage of mu tilde is that mu tilde is a martingale. And because it's a martingale, that's a very, 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 very important property. There are a lot of things happens which are nice for this homogeneous case when all the cubes are retained by the same probability. So here we utilize on the fact that we have only one retention probability P. In the more general case, it doesn't hold, and second part of my talk will be about the more general case when this property does not hold. But in this homogeneous case, where all retention probabilities are the same, in this homogeneous case, this mu tilde measure is a martingale. And because this measure is a martingale, using that, Michal-Rams and Yuval Perez proved a very interesting theorem that if the dimension of this Mandelbrot percolation is bigger than 1, then the projection of mu to all lines simultaneously, these measures are absolute continuous, even with Hölder potential if you do not project to the coordinate axis. So this is a stronger theorem and a very, very nice theorem. And using the idea of this theorem, Suomola and Schmerkin wrote a very, very long paper. I think it's almost a book where they proved zillions of important and interesting statements for random sets where this martingale property holds. I just like to mention one of their results. In order to do that, I need to say what is the slice of a set. I explain it. This is a triangle. This triangle is a set. And then what do I mean a slice? So for the slice, I need an angle, which is this angle of the line. You see, this is an angle of the line, and this theta is the angle, and x is a point on the line, and corresponding to this angle and x, there is this red set. What you see over here, this red set is the slice. So this is the intuitive definition of slice, and the official definition is written, but I believe everybody knows now what is the slice, so maybe I can go ahead. And then Schmerkin and Suomola says that for all theta, which are not the axis, so their axis, when this line, what I show here, this line is neither of the coordinate axis, then there exists a non-empty interval on this line, on this L theta line. There exists a non-empty interval such that whichever x you choose from this non-empty interval, the corresponding slice has the dimension, which is the dimension of the set itself minus 1. So this is the correct dimension you would expect. So it happens simultaneously for almost all realization and for all theta, for all elements from an interval. Of course, it cannot happen for all x because it can happen that the slice is simply an empty set. But there is an interval for which this happens. So that's a beautiful theorem, and also shows that when you have this homogeneous situation, then everything is really marvelous. And we also had one more theorem with Michal-Rams, in which we considered mappings from the plane to the line, which are strictly monotonic. This means that strictly monotonic, for example, these mappings are strictly monotonic and smooth. So F is smooth and strictly monotonic, and P is big enough so that the dimension of the set is bigger than 1. Then the image with this function, the image of the Mandelbrot percolation contains an interval. So in this case, the sum is the 45-degree projection, basically. And we already know that this is true for all projections. So this theorem is a kind of generalization of the previous theorem. And even if you take this product, you still have, or any other functions for which this condition holds. So this was basically what I wanted to say about the homogeneous case. And the essence of the homogeneous case is there are many theorems which shows that you are in the homogeneous case, and the dimension of the Mandelbrot percolation set is bigger than 1. Then in every possible projection, there is an interval, or the slices behave as they need to behave. So everything happens as beautiful and organized as they can. So the next question was, what happens if you take a kind of inhomogeneous situation? And I would like to explain what is the inhomogeneous situation, but in order to do that, I need to go back to this definition. Originally, we had just one coin, but in the inhomogeneous situation, for each of the positions, so in this situation, you have one coin. So in this situation, you have not one coin, but you have 9 completely different coins. And these numbers, what I show over here, gives you the probability that these coins will land on head. So this is the retention probability, but at different geometric positions, the retention probability are different. We assume about these numbers that they need to be smaller than 1, but interestingly, they can be 0 and they will be 0. I will consider only cases in this talk where these P's are either the same, Pij are either the same P or 0. So I will distinguish only 2 probabilities, the 0 probability and the non-zero, but if non-zero, then all non-zero probability will be the same number. So you are given, but in the general definition, you are given just 9 probabilities. You can understand that these are 9 different coins. They are all bias coins, but bias in different way with different probability bias. And then you toss this coin, it results something. And then within that, you just say, so this always refers to the left upper corner. And this coin always refers to the right bottom corner. And then the probability that the left upper corner is head is this number, and the right bottom corner is this number, whichever scale you are at. So when you decided that you retain this, then it happened with this probability, you retain this with this probability at the bottom right bottom corner, and then on the next scale, you use the same. So the left bottom, this coin is related to always to the next bottom corner, left bottom corner, wherever you are at. So this is the inhomogeneous fractal percolation, and I would like to ask you if you have any questions related to that. Is it clear? So here we have 9 different coins, which results in head in with 9 different probabilities. Is this clear?
But if it's for all levels?
All levels, yeah, for all levels, in all levels, whichever level you are at. For example, you have already selected this, and then on this level, you would like to decide whether you retain this square, the left upper corner square, whether you retain or not. Then you toss the same coin. This coin is the one which lands on head, with P02 probability. It doesn't matter which level you are at, or either you are at the 0 level when you decided whether you get this big one, or you are on the next level when you decide that you retain this square. You always toss the coin which lands on head with this P02 probability. Is this clear now? Yep. So you have altogether 9 coins, and you use that 9 coins in this arrangement on any level. If you go to level 1 million, you still use exactly the same collection of 9 coins. Is this clear now?
Yep.
Okay, so this is a question. Yes.
Is there exist some relation between this set and infinity Bernoulli convolutions?
Bernoulli convolution, I don't know. I do not see any. In particular, not this inhomogeneous. Nothing comes to my mind right now. So this is the inhomogeneous case, and there are a number of papers, Decking, Grimet, Falconer, Decking, Mister, Falconer, Grimet, and lastly, Borel, Feng in Advances in Math. No, there's some French last year. So there are many papers. I would not like to speak too much about that, but they are. And we would like to consider, as I mentioned, those cases when either, so there is a probability such that all probabilities among these probabilities which are not 0 equal to that same probability P. So the easiest situation is, or the most well-known situation is when we consider the random Sierpiński carpet. This is the random Sierpiński carpet case because we retain these people which are not in the center with probability P, but we always throw away the central element. This is very similar to the Sierpiński carpet. If P was equal to 1, then it would give you back the Sierpiński carpet. So this was considered for the birth by Decking and Grimet, and they wrote a paper about the projection to the coordinate axis of this set. Now, here we proved with Lajos-Vágó we considered this example, and that was a place which showed already that even in this simple situation, it's no longer true that the fact that the Hausdorff dimension of this two-dimensional random set is bigger than 1, it does not imply that in all projection you have an interval. Because if you consider this set, if you choose a P which is bigger than 3/8, then the Hausdorff dimension is going to be bigger than 1. Why is that true? Because the Hausdorff dimension is logarithm of the expected number of children divided by logarithm of the reciprocal of the contraction. Now, the expected number of children, you have 8 cubes or squares, and each of them selected with probability P. So this is going to be bigger than 1 if 8P is bigger than 3, which means that P is bigger than 3/8. So this is the threshold for having dimension bigger than 1. On the other hand, with Lajos-Vágó, we proved that if you give me any number k is a number, it can be 1 million, then we can find a P which is slightly bigger than 3/8, and we can give you k different angles, alpha 1, alpha k, such that the projection in these directions are empty almost surely. So this is a different phenomenon, but we have seen in the homogeneous case. Okay. And then we considered another example, as opposed to the previous one. Here the probabilities in the first row and the last row are P, and all the probabilities in the middle are 0. So you see that if you project this set to the y-axis, then whatever you get, it will be a subset of the triadic Cantor set. So whichever P you choose, even if you choose P is equal to 1, it doesn't give you an interval. Here you have 6 squares, so the expected number of squares chosen after the first step is 6p. This is the dimension in this case. So this is the dimension, and what we prove it was that if alpha is in this range, then there is an interval almost surely, and of course there is no interval if you project to the y-axis. So there is an interval where for all elements simultaneously in the same time you have interval, but there is an exceptional, trivial exceptional angle. So that's also an example which shows that not exactly the same thing happens for the non-homogeneous situation. And with Vilma Orgoványi, and this is the moment when I start to speak about the new result, with Vilma Orgoványi, we wanted to understand what about the projection of the random Menger sponge. So what is the random Menger sponge? You just consider what is the deterministic Menger sponge. You take the unit cube, and then you divide it into 27 cubes of side length 1/3, as it is shown here. And then you take away this red something, what we didn't know how to call it. If you have any suggestion, a good name, we called it Quasimodo. So we call Quasimodo this kind of object that you see on the right-hand side, and then we remove from the cube this Quasimodo, and then there remains, this Quasimodo contains 7 cubes. So after remaining 7 out of 27, there remains 20 cubes, and then this is the first step, and within each retained this is deterministic, so we deterministically remove this 7, and then we repeat the process in every retained square, and you see the approximation of the Menger sponge. So we studied this, actually the random Menger sponge. What is going to be the random Menger sponge for each cube? And I hope it will be clear. Please tell me if it is not clear. So you have here 20 cubes of side 1/3, and then you take just one coin with probability P, it lands on head, you toss the coin, and if it is head, then you retain this cube actually. If it is tail, then you throw away this cube, and then there will be nothing in the future in the place of the cube which is removed at any stage. And then after one step, there remain some cubes which are retained, and within that, we repeat this process as we did previously. And similarly, as previously, like this random Sierpiński carpet, we get similarly the random Menger sponge. Is the definition clear? Is the definition clear? We run the same random process. What we did for the unit square at the beginning, for each retained level and square, you divide that into 27 small squares. There will be a picture about this. So this is the cube, and then you divide it into 27 cubes of side 1/3. and each of the cubes, and among these 27, you remove the Quasimodo, and after the Quasimodo, you have this, and then you have 20 cubes, and for all the 20 cubes, you flip the coin, and let me say, these are the 2 lucky cubes which we retained. All the other cubes we needed to throw away. And then what we do in these 2 cubes, we divide both of these retained cubes into yet again 27. We remove the scaled Quasimodos in each of them, and yet again we flip the coin, and let me say we end up with this, and we end up with this, and we repeat this process. So this is going to be the random Menger sponge. Do you have any question about the definition of the random Menger sponge? So this is an inhomogeneous situation because the Quasimodo is always thrown away, so it is retained with probability 0, and all other cubes are retained with probability p. So there are 2 different probabilities, but this already causes interesting. Now we would like to take the projections. So we use the notation projection ABC. This is the projection. So for example, if you want to project this diagonal of the cube, which we will do because this is easy, I mean, formulas are going to be easy. So if you project that, then this is 1, 1, 1. This is the projection to this main diagonal of the cube. And then let me show you the picture, but now I need to go. So is it clear what we are doing? We project sometimes to this diagonal, and we project this random Menger sponge. But I go to another screen because I would like to show it on a bigger scale, because it will be difficult to see. It's too small now. So we are here. Okay, I show you. It's very much different what happens. So we start from here. This is P. So on this, here is P. P is running here. Okay. So one thing that we proved it was that if P is bigger than 1/4, then the random Menger sponge, this projection for any direction, whichever direction you like, then any direction simultaneously for all direction, for almost all realizations, simultaneously for all direction, there is an interval. If P is bigger than 1/4. Now, if P is not bigger than 0.35, then MP is totally disconnected. So if you choose a P from this interval between 1/4 and 0.35, then for that P, this random Menger sponge is going to be totally disconnected, which is a random dust, but its projection to any line, simultaneously to any line, does contain an interval. Now, this is just an obvious statement that if the probability is less than 1/4, then when you project to the coordinate axis, then you do not have intervals. Now, here is an interesting statement. If the probability is bigger than 0.15, maybe there are some more digits, I don't know, I forgot, but nevertheless, approximately 0.15, then the Hausdorff dimension is bigger than 1 conditioned on non-extinction. So have a look at this interval between 0.15 and 0.25. If you choose a P from this interval, what happens then? Then you have a Hausdorff dimension bigger than 1, but you do not have interval in every direction. So it doesn't happen in this case, as opposed to the homogeneous situation, when Hausdorff dimension bigger than 1 implies that in any direction you have interval. It doesn't happen here, but there are some little other interesting things. So all until now, I spoke about in general projection, but from now I will speak about the projection to this main diagonal of the cube. So the projection of this main diagonal of the cube on this interval from 0.15 to b, which is a number bigger than 0.15, the Lebesgue measure is going to be 0 here. And then there is another interval. So this b is in between 0.15 and 0.166. Here, the Lebesgue measure is positive, but there is no interval as far as this projection to the main diagonal is concerned. So here the Lebesgue measure positive, Lebesgue measure of the projection to the main diagonal is positive, but it does not contain intervals. And then this is the interval, the 0.1166, whatever. So if p is bigger than that, then the projection to the main diagonal does contain interval. So these kind of things can be pointed out. So in summary, if you want to guarantee that the random Menger sponge has interval in all possible directions, then you need to require that its Hausdorff dimension is bigger, not only bigger than 1, but you need to require that bigger than 1.46, whatever. So it needs to be quite big in order, because it's inhomogeneous. So that's it has a different structure. So now I would go back to the other screen. Okay. So this is just the iterated function system which gives you the Menger sponge. This is 1/3 x plus the translation. When the translation are all possible translation except the coordinates of the Quasimodo. So the coordinates of the Quasimodo are named over here. These are the left bottom corner of the Quasimodo. Okay. And then this is the projection. So this was the set itself, and I go to the projection 64. So how do you get the projection to a certain line? You need to project these translations. If you take the projection of the translation and the same contraction, it gives you the projection to the line. So if you want to have a simpler view of this, then this is what happens. These are the for the random Sierpiński carpet. This happens. We will come back to this a little bit later. Okay. This is just repetition what I have already said, and I still have a little time, so I would like to tell you what we really do or how we prove all of this. We consider more general setup. So here is a self-similar set, because if you take the projection, any rational, it's important rational angle projection of a carpet to a line, then after rescaling, what you get, it is an iterated function system like this, when this is 1 over L, this is 1 over an integer times x, but the same. So this multiplicative part is the same, and this is a reciprocal of an integer, and ti is from a certain lattice, but after rescaling, we may assume that this lattice is actually so it is. These are just natural numbers. We may assume that, and some of these mappings can be the same. Just because if you project down, then through the projection, even if the mappings in space are different, but after projection, they can be the same, and nk means somehow the number of those. So we arrange these mappings in such a way that the first little m will be different, the first little m different, and the rest are equal to one of the first little m. And so we can assume that these translations, we can assume that the first translation is 0, and then these are all placed in this way. And then here is a technical assumption that L minus 1, L is the reciprocal of the contraction, L minus 1, so Tm divides by L minus 1, just we rescale sufficiently, we multiply it with a number, it doesn't matter, it doesn't cause any problem. So for example, in case when we project the Mandelbrot, the Menger sponge, then L is equal to 3 and Tm is equal to 2. We will come back to this on a certain example. I believe there will be an example soon when I can explain everything. That there is a very important thing which is these matrices. So there are two kinds of matrices. The most important role is played by these expectation matrices, which are just p times bigger than these B matrices. And so what are these B matrices? So BLK is equal to Ni if there is a mapping Si which sends, so what was JK? JK is a basic interval. Probably it's better if I immediately show it to you on a certain example. I think the best, if not in general explain, because then there will be too many definitions. So assume that we do not consider the random Menger sponge, but the random Sierpiński carpet. And then here are two possibilities: that you take the projection to the coordinate axis, or you take the 45-degree projection, which is the simplest among all projections which are not the coordinate axis projection. Now, if you project for technical reasons, we do not, this is not the unit square, but this is basically the square from 0 to 3, but just for technical reasons. So as far as basic intervals, if you project to the coordinate axis, then you have only one basic intervals. If you project to any other axis, then there are more than one basic intervals. In this case, the first basic interval 0 to 3, this is J0, and the second basic interval is J1. Okay, so these are basically the types, because behind all of these, there is a branching process, a multi-type branching process in random environments. So this is the probability background, and multi-type because we have this is one type and this is one type. You can imagine that when you project, then either you project this kind of triangle or you project this kind of triangle, and on each scale, and then you are interested in how many children of such a triangle, how many children it has in terms of these down-looking and upward-looking triangles. But the point is that you need to take it in a specific environment, so it's more complicated. But the point is that here there are two intervals which gives you the types. These are the two basic intervals, J0 and J1. These are the two basic intervals. Now, when you take this projection, so this is the iterated function system. Better to talk about the 45 projection. Then when you take this projection, what kind of mappings you have here? So here there are 8 squares. You project them down, and you see that this square will come to this interval. However, when you consider this interval, then there will be 2 squares which project into this interval. 2 squares project into this interval, namely this square and that square. And that's why this number little n is going to be 2, and the same happens with with this middle intervals. So the intervals in the middle, there will be two squares, and these numbers are n. So n1, n2, n3 are equal to 2. But if you consider the intervals at the two sides, then there are only one square, which totally mapped onto that. And then we form the matrices. These matrices play a very important role. Basically, the ones which immediately applied are these expectation matrices, and you just multiply this matrix by P to get the expectation matrix. So how do you compute this matrix? It is written over here. Let me explain you why it is true that this value is equal to 2. The one here at the right top corner, why it is equal to 2. So this A, what you see here, A, it can be anything from 0, 1, 2, because we always count everything from 0. So this A can be 0, 1, 2, like 0, 1, 2. So when we talk about this matrix, then it is 2. And then here is this L. This L, it can be either 0 or 1. In our case, when we are in this, then it means that L is the first row. The first row means L is equal to 0. So L is equal to 0. It means that we are within this big interval. We are within this big interval. I want to see if you have already seen now within this big interval. And within this big interval, because this is 2, we are in this last bit, the last 1/3 part of this big interval, okay? This is, we have spoken about the fact that we are in this line, and we consider B2. Now we speak about that we consider the last, so that this is equal to 1, because we number the columns as 0 and 1, so this is 1. So it means that we would like to get this little interval here. I like to see if you see it. Just a moment, I need to wait. Yeah, so this little interval as the image of this interval, which is over there. I need to wait until you see it. Now you see it, I hope. And then it happens with this S1, and this S1 is realized, the S1 is realized as the projection of two squares, n is equal to 2. That's why you write here 2. If there was no way to realize it, then you would write 0. So this is the way to write down this matrix. And sometimes we consider their sum, and their sum is actually a primitive matrix always, but it's not important. So these are the matrices. These matrices will determine everything for us, and all the results are stated in terms of the matrices. Now I would like to show another example. The easiest example is if you take the right-angled Sierpiński carpet, then with probability P, you choose these gray squares. So the deterministic right-angled Sierpiński carpet, these are the first 3 approximations, and then you have this probability P, and you choose everybody independently with probability P, and you play this usual. And then what are going to be the basic intervals? Here, this is one of the basic intervals, and this is the other basic intervals. So you have 2 basic intervals, and the contraction ratio is equal to 2. So you have 2 matrices, both of them are 2 by 2, and these are the 2 matrices what we have. So this is the way to write down the matrices for, and then we consider this coin tossing, they call it coin tossing self-similar set, when you use these parameters here, and then at every level and step, you decide which children of a red level and intervals survive just by coin tossing, as we have done all until now. So we have a couple of results. which I do not have much time, so I would not read out too precisely, but with Vilma Orgoványi, we proved that under some conditions, which are checkable conditions and which are related to this matrix, I told you what is B, and M is just P times B. So under some conditions, you get that you have an interval almost surely conditioned on non-extinction. These are checkable conditions, but the result is not very precise. I mean, this is not if and only if type statement. And there is another one which is about the positive Lebesgue measure of the set. Similarly, we just need to examine these matrices, and then some properties of the matrices imply that the Lebesgue measure is positive. And when I mentioned those results about the Menger sponge, that it can happen that for some direction, the projection has zero Lebesgue measure, but sorry, positive Lebesgue measure, but does not contain interval, then we use this kind of theorems to prove that. So originally we prove everything in this generality for this kind of random self-similar sets on the interval, and then we set some conditions, and we want to check these conditions, what kind of probabilities it gives for certain. But this is a dynamical system seminar, so I would like to give some more insight how to prove something like this. That will be a different theorem. I have maybe 10 minutes for that. So I would like to come. Now I would like to speak about the fact that in this inhomogeneous random Cantor set, it happens under Meyer condition that the carpet has Hausdorff dimension greater than 1, the carpet, but the projection has dimension less than 1, almost surely. So I mentioned this, that this phenomenon can happen, and we would like to prove it. And most of the proof was prepared by Dae-Jung Feng. I mean, we just used theorems which were reformulated and made it easier to understand by Balázs Bárány and Mihály Rams. So I am going to refer to that during the remaining 8 minutes. So what I just like to write down yet again the setup. So we are on the line, we are given an iterated function system. This is a deterministic system, but some of the mapping, so they are not distinct. The contraction ratio is 1 over L, but among the translations, the first M counting from 0 should be M minus 1. Sorry, it is not M minus 1. Counting from 0, the first little M minus 1 are different. And the last one, this is M minus 1, should be a multiple of L minus 1. This is not a restriction. You can always multiply with a number. So you can achieve this as soon as these translations are rational numbers. You can achieve that. And then we consider the basic intervals, what I have already explained, what the basic intervals are. Like in this situation, as I mentioned, when you project to the coordinate axis, then there is only one basic interval. Otherwise, there are always more than one basic interval. We need an assumption, a little bit complicated assumption. There were this Nj. Nj tells you how many squares project upon such an interval. So N0 is equal to 1 because there is only one square, but this is S1, and there are 2 squares which project here, this one and that one. Therefore, N1 is 2, and N2 is 2, and N3 is 2, and finally this is 1. So these are the N's in this case, and you form the ratio between Nj. N is the number how many squares come to a certain interval, and capital M is the number of all squares. So you take this ratio and you make simplification such that the numerator and denominator has the greatest common divisor equal to 1. Then you get what is Lj. In our case, these ratios are either 1/8 or 2/8. So the least common multiple of these numbers, which are each either 4 or 8, the least common multiple is equal to 8. And the condition is that here L is the reciprocal of the contraction, and this happens. So L does not divide R in our case 8, so it happens. So this is the assumption in this special case, and if this assumption holds, then the box and in this way the Hausdorff dimension. So you have M, which is the number of squares, and this is bigger than L. This assumption makes it possible that here in the space you have a set of dimension bigger than 1, and this is this technical assumption what I explained over there. Then you can choose a probability which is bigger than L over M. L over M is smaller than 1, so it's bigger than N over M, and the corresponding set has a dimension smaller than 1. So in this situation, what you have for such a P0, because P0 times M is bigger than L, that's why this carpet has dimension bigger than 1, but the projection has smaller than 1, and this can happen only for this inhomogeneous case, because in homogeneous situation, the projection, if you have if the carpet has dimension bigger than 1, then the projection has interval, contains interval, but here it is quite common. In the inhomogeneous case, it's quite common that not only the projection doesn't have interval, but the projection has dimension smaller than 1. Now, here is the dynamical systems. What I have just a very few minutes for the dynamical systems. These are these very important matrices that I mentioned. Everything depends on these matrices, these B matrices, which were defined over there. And also these matrices appeared like here. So you take these matrices and then you consider their product, and in this usual way, you form the pressure function. And the value of the, I need to go a little forward, maybe 81 is here, and go ahead. So this pressure function look like this red, what you see, this red curve. So the value at 0 is 1, and the value at 1 is equal to log M over log L. This is bigger than 1. So this is how it looks like. It is easy. This is the easy property, but there is a very much not easy property, and everything depends on that. It is drawn in a way, you see this red curve, it goes down. So this black line has slope s minus 1. And the way as I drew this curve, it says that the derivative of this curve at 1 has, the derivative is bigger than s minus 1. And indeed, it's very, very important. And that is a crucial, step to prove that, and that proof comes from Dae-Jung Feng and Balázs Bárány and Mihály Rom's works, so that this slope is bigger than 1. So this red line, this red curve, this T to PT curve really looks like that. Because then if you take the Legendre transform, and the Legendre transform at S minus 1, the Legendre transform is this point. So from this, it follows that even if that you can find somehow, I do not have time to complete everything, but somehow the crux of the matter will be that you can find an alpha which is smaller than S minus 1, such that the Legendre transform, this is the Legendre transform for S minus 1. But if you take an alpha, which is close to S minus 1, just a little bit less, then this green line, which has slope S minus 1, then instead of S minus 1, it will have a slope less than S minus 1, not much less. And then still the Legendre transform will be less than 1. And if the Legendre transform is less than 1, then with some technical steps I don't have time for, it follows that this claim, what I stated here, that we can find this P0, which is bigger than L over M. And in this way, because it's bigger than L over M, the carpet on the plane has dimension bigger than 1, it's bigger than L over M. But for this alpha, the Legendre transform of the pressure is smaller than 1. And because of that, the projection set has dimension smaller than 1. So this is the way as dynamical systems comes into this geometric measure theory. And there are many other assertions, and most of the proofs are more related to probability theory. We had the least contribution to this statement because it almost immediately follows from Dejun Feng and Balázs Barány and Mihály Rams, but this has the most thing to do with the dynamical systems. That's why I wanted to speak up. Thank you very much for your attention. I finished.
You have questions?
I have some questions about the generality of this method. I didn't quite understood. So at the end, you consider the case when Pij or all are equal to either 0 or P, right?
Yes.
Does your method apply to obtain some results in case when this is not true, when you have distinct Pij?
No, but I have to tell you a very strange story. When I was in Warsaw during the last Simon's semester, I was there for 4 months, and I wrote down into my exercise book something that for some important reasons, only these are the important cases. So somehow when you have different Pijs, and then somehow there is a threshold that those which are bigger than 1 count because the other somehow dies out. But unfortunately, I lost that exercise book. I didn't bring it back to Hungary. So I cannot give you precise statement, but somehow those thinking what I made in Warsaw 7 years ago or more somehow showed me that this is an important special case when you have all probabilities. So all probabilities which do not reach a certain threshold, you consider 0, and the rest you consider this threshold somehow. And then you can approach that. This is what I did. I remember, but I don't even remember the precise statement. So that's why I was, and somehow I wanted to, well, not I, but we wanted to show with Vilma Orgoványi, with whom all of these results are joined, that we proved with Mihály Rams, and then Mihály with Yuval Perez and Sommola and Smerkin, that if you are in the homogeneous situation, then everything is as nice as possible. And we wanted to show that when you are even in this slightly inhomogeneous situation, when all probabilities are the same, which are positive, this is the most regular inhomogeneous situation. Even in that case, totally different things happen. If you think of what I showed in this situation, you see all kinds of bad things happen. Things are as bad as possible, as opposed to this, if you are in a homogeneous, then in the space, something has dimension bigger than 1, then in the projection you have interval. So as simple as possible in the homogeneous case, and even in this not very much inhomogeneous case, it just breaks down.
I see. I wonder about the angle theta. So in the proof you showed, did you consider theta equal to pi over 4, or it is for general?
Pardon, pi? Pi over no. This is general. That the proof is so the proof is general because the proof is not set exactly. This is just an illustration.
I see.
This general in the sense that the projection angle is a rational angle, because if you have a rational angle, then multiplying by a sufficiently high number all translations, you have that all of these translations are integer number, and even integer number which satisfy this condition. So these are about rational angle projections, but more general than rational angle projection, but include the rational angle projection.
I see. Great, thank you.
Thank you.
Well, if no one else, and I have one more question. What about the number, the dimension? Is it for plane, or is it also applied for higher dimensions?
No. The dimension. If I understand well your question, let me go to a very special case. Do I understand well your question that you choose a P in a way that the projection has 0 Lebesgue measure, and then we may ask the question, what is going to be the Hausdorff dimension of the projection? So you choose a relatively small P for which you do not expect to have positive measure anything here, just the Hausdorff dimension. Now, let me tell you the answer. We do not know the answer, but I do know something. Basically the following, that if you have this random Sierpiński carpet and you project it, this very simple thing, you project it to the coordinate axis. You just project. The Hausdorff dimension in that case is computed by Decking Grimet in a joint paper, and then Falconer, who extended it and simplified it and whatever, but it is not trivial at all. And they use branching processes in varying environment, and we need the same with multi-type branching process in varying environment, but we have not yet done that. So we have this theorem, but I mentioned over here, which theorem says that the conclusion of the theorem is that the dimension is smaller than 1. We just managed to get this kind of, that the dimension is smaller than this, but this number is smaller than 1, then we can get that the dimension is smaller than 1 somehow. But this is just an upper bound on the dimension. We do not have a formula for the dimension. Even if you project here, you have a rather strange formula. It is like infimum for all s, and then you take the t's power, s power of the expectation of how many squares you have, the sum of the expectations of how many squares you have in a column. So it's a little bit, not a direct formula, which is easy to evaluate, even in the case when you project to the coordinate axis. We are very much interested in working on what happens if you take a rational angle projection and P is small, so the projected set has dimensions smaller than 1, then what is the projection exactly? It will be mostly probability theory, mostly multi-type branching process, multi-type varying environment, this kind of thing.
Dimitrov has a question. Dimitrov, go on.
Yes?
Yes, I have a question, Professor. Thank you for the interesting talk.
Thank you.
I want you to ask you about topological type of the projection. slide number 61. As you
61, just I go to 61. Yes, it's here.
61, yes. As you say, it can contains interval. So I mean, it can be a finite union of intervals or infinity union of intervals or contourval, for example. Some.
I have to tell you that we do not know that. Because I tell you what we did very, very briefly. We had this paper with theorems on the plane, and we extended it with Lajos-Vágó to higher dimension. And in that paper, there is a certain condition in Michal. With Michal, we called it condition B, and it needs to be checked, and then you get this conclusion. This condition B was generalized to higher dimension. We checked the condition B, and it is just like that. So it's I do not remember, Michal, that our paper on the plane would give answer to this question. It just proved the existence of the interval, because whatever happens here, it is just the generalization of that original.
Probably existence of the interval means existence of infinitely many intervals, because if you go to any small interval outside this interval, then again you have positive probability of having interval there. So I kind of expect that theorem, each of our theorems stating that there exists almost surely an interval, means that almost surely there exist infinitely many intervals.
Yeah, yeah.
At least when we are below the critical probability. Maybe above is just one interval going all the way.
But not more. So I don't think we ever thought about contourvals or this kind of things. So
So it can contain interval, but not to be a finite union of interval, for example. Yes.
It's highly unlikely. Maybe it can be proven that if there is, as Michal says, if there is one, then there should be infinitely many. That's what I would bet on. I would be surprised if the answer was like, with positive probability, you have finitely many intervals, but more than one.
Interesting. Thank you.
Thank you.
Thank you. Thank you. Goodbye. Then I stop.
This is for people who are here. They are not all eaten. See?